let's look at a special case for elimination, huh? Let's look at a special case here. So, wait, not elimination. I meant substitution. I mean, you can easily do elimination on this one just by multiplying this one by -2, because then those would be opposites. However, let's just look at it with substitution. So we know this is going to be a special case because I told you. But let's just go ahead and solve and see what happens, and then we'll interpret. So I'll use this one because remember I want to solve for, it's easiest to solve for a variable that has a coefficient of 1. So I do that, and I will have negative 7x plus y. This one will go a lot faster, I think, because I'm going to explain less. Add 7x to both sides. Those are not like terms, so I can just write 7x plus 19. Great, take that, plug it into this. Whoop. So I would get negative 14x plus 2 times 7x plus 19 equals 38. Distribute. That's very nice. Negative 14x plus 14x. Oh, look at that. Look at that. Yeah? And then 2 times 19. What's that? That's 38, isn't it? 2 times 19 is 38. Plus 38 equals 38. Now, I combine like terms. Those cancel out because one's negative, one's positive there. And so I just have 38 equals 30. What? 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 Oh, that's a... whatever. You understand. It's oh my goodness. So this is true. This is true. This is true. So our answer here is actually that there are an infinite number of solutions. Infinitely many solutions. So I'm going to write that down. Infinitely many solutions. Soluciones. Infinitely many solutions. That means these lines intersect each other at an infinite number of places. They intersect each other at 10 places and also 13 places, 87 places, as many places as you can think of. They intersect. Just there's some specifics, and I'll show you. I'll show you why. So this is the why part. Why? Well, let's graph them. Because remember, the whole entire idea behind this is that the solutions are where the lines cross, or where they're the same. They share the same ordered pair. So let's take a look at this negative 7x plus y equals 19, and I'm going to get into y equals mx plus b form. Y equals mx plus b. All right, so that means I'd move the 7x over, plus 7x. So I just get y equals 7x plus 19. Oh, that's fantastic. So I could graph that if I wanted to. I could graph that right now. What about the other equation? Let's start with black on that one. The other equation is negative 14x plus 2y equals 38. So if I take a look at this and I'm trying to get it into y equals mx plus b, I would add 14 to both sides. Or sorry, 14x to both sides. And that goes away. I have 2y equals positive 14x plus 38. And then remember, I want y all by itself. So I'm going to divide everything by 2. So that goes away. I have y equals 7x, right? 14 divided by 2 is 7. And 38 divided by 2 is 19. What? What? They're the same line. That's why there are infinitely many solutions. Because they're the same line. If I were to graph them, one of the lines, well, it'd be up positive 19 and then rise 7 over 1. It'd be something like this. So if I graphed that line, that's what it would look like. If I graphed this line, you know what it would look like? Right on top. So where do the lines intersect? Well, they intersect here, and 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 here. At every point on the line, they intersect. And this goes on forever, and forever in that direction as well. So there are infinitely many solutions. You just choose a point that's on one of the lines, and it'll be on the other, because they're the same line. Alright, so that's that special case. Let's be clear here, though. Just because I'm using substitution doesn't mean that this special case only works for substitution. It could happen in your elimination cases, or it could happen in your graphing cases. They're just easier ways to solve based on how the equations are set up, whether it's by graphing, elimination, or substitution. I'm done. Peace.